Okay, well, here we are again. I did a video a while ago trying to talk about the principled shader, and there's a lot of people that did a lot of videos about the principled shader when it first came out. And some of the settings bothered me. There weren't too many, um, I guess, in-depth explanations about what was going on with the principled shader. Um, a lot of times when the first implementation of something comes out for Blender, people are already trying to use it right away and trying to explain how this works and that works, and they get piecemeal type of explanations for what is going on. And I also noticed that there are some scenes or textures or whatever that they throw on it that might obscure the subtleties of what it's actually doing. They come out with great results, but we don't really get an understanding of what it's doing. And so what I thought I'd do is I'd just go ahead and take this opportunity to explain a little bit more about the principled shader as far as what I can understand, because it's based on the Pixar Disney shader. And so what you see over here is I have both of these things lined up. We have Pixar Disney on the left side, and we have the principled BSDF over here. Disney calls theirs a BXDF. There isn't really much difference between the two. And as you can see, what we're looking at here is that it's almost the same layout for both of them, and you can see that the titles are pretty much the same as well. But the Pixar Disney shader has an emit color for an emission material, and you have down here a transmission material, and you have some more normals down here and stuff like that, but they're pretty much the same. The unfortunate thing is that if you don't go out and download the non-commercial version of RenderMan, you probably don't understand what these do, because it says input value used for unconnected socket. You know, for most of these things. Well, it doesn't really give an explanation. PicsArt is really good. I've actually read into some of their code and stuff like that, and everything's commented out about everything that they do. And they put in really good tool tips for everything that they put in here. It tells you how to use it and what it's used for. And since the development team is actually trying to implement this version of a shader into here, and it works almost identically, it's good that I actually downloaded it and got an idea of what these were. Now, Disney and Pixar and studios who use RenderMan can use two different Uber shaders. One is this Pixar Disney, and the Pixar Disney is kind of a new implementation for them, because they're using this metallic roughness bump and BaseColor, the PBR approach on this. And then the other one's like a Pixar Surface, which has traditional specular inputs and stuff like that. It's much bigger, and you can activate and deactivate lobes as you need to. So you can see that this is only going to drive diffuse, so then we have a specular, rough, clear coat, iridescence, fuzz. All this stuff just keeps on building and building and building. This is the Uber shader of Uber shaders. But generally, right now, this is going to give you a faster workflow. And I think it gives it a more predictable workflow and can allow you to turn things out much quicker. RenderMan's tried and true. It's used in all your favorite movies that you see, from Avengers to X-Men, Star Wars, and anything that Pixar does, obviously. Has a long track record, has a really large development team spread over, like, I don't know, 4 countries or something like that. It's no wonder that people try to emulate some of the stuff that they do, and they do a lot of their research where they do it carefully, except for probably in Big Hero 6, where they used a render engine called Hyperion, which actually was an alpha stage when they did the movie. But it allowed them to render things much faster, and hopefully that tech makes it into RenderMan. But I was doing a project, and I decided to use RenderMan because there was a lot better light fall off and a lot better shadow depth. And I had to play around with the settings eventually in Cycles because I'm like retopologizing all this stuff anyway. Cycles is much faster than RenderMan, even in CPU mode, and has an equivalent denoise system that RenderMan does, so you can lower your samples. And so I wanted to figure out how to do it, and I think I settled on some settings to do it. And I'm using the principled shader because I was using the Pixar Disney or the Surface shader in the project anyway. And basically it's just a one-on-one translation. You're going to use the same texture maps and everything like that, and you're going to get the same response. The only thing that's going to be slightly different between RenderMan and Cycles, as far as their output is about the settings in the render and how many bounces and stuff like that. So that's where the difference lies. As long as these things are set up the same and then you set them up equivalently in their render engines, you will get an identical response. I kid you not. It is pretty much identical straight across. There is really little difference in between them. Like I said, out of the box with default settings, RenderMan renders a hell of a lot better than Cycles. And in some cases, it can render some things much faster than Cycles in CPU mode. But they're researching GPU and RenderMan. I don't know why they don't implement it. Probably because of the same old problems that we have in Cycles. If we're using GPU accelerated stuff, there's only so many textures that we can load in, and there's only so much geometry that it can hold on the card, so you'd eventually have to default the CPU. But for right now, from one of the tests that I did, Cycles is actually faster than RenderMan. In scenes where you have stuff in the background back here, but if you don't have a background, like I had turned this ray visibility off, RenderMan will be comparable, if not faster than Cycles in this type of a mode. But if I were to turn the environment back on and it had to do this over and over again, what it does, what that Cycles doesn't do, is it does adaptive sampling. So after it's figured out that this is all within a certain variance, it'll just work on this part. But the denoise process takes a long friggin' time for RenderMan, even though they've increased the performance of it. Cycles is much better at denoising it. Denoises on the fly, and it doesn't really need adaptive sampling to speed it up. It is just much quicker. So enough about that crap. Let's get into the principled BSDF here. Basically what we're going to do is we're going to go for a top-down approach and look at mostly everything. Just a couple simple examples. Like I said, I don't want to have anything cluttering this thing up. We're not going to add a normal map to this because everybody pretty much knows what a normal map does. It's the same thing in your other node networks and all throughout other renderers anyway. We know what a normal map does. Okay, as far as these different settings, this normal affects the surface of the object. The clear coat just affects the clear coat setting here, and the tangent I haven't got to work yet, but there are, you have tangent space networks. There's one thing that I have to say is that you do not have to add in mapping or texture coordinates for any of this, as long as your stuff, if you're going to apply maps to this, like in the base color, you can even apply it to subsurface color or any maps here. What you're going to do is you don't have to use the texture coordinates or the mapping coordinates anymore. It's going to automatically look for that particular UV map for that object. So all you have to do is just plug the map into it. That's it. You just fire and forget. Just put in your texture map, load in a texture and go boom. Put it in there and it works. Same thing with the RenderMan. That's what I loved about it. I'm like, where do I find all this UV stuff? How can I set it? It's already there. It's looking for it. It's already loaded up. It's right there. So right away, your node network got a hell of a lot smaller. All you're going to have is like texture, like texture for the base color, texture for, let's see here, roughness, and then you're going to have a texture but one additional node for a normal map. You're going to put your normal map node in there and then plug it into the normal. And really, to drive any surface, that's all you really need. Okay, everything else, or another texture for the metallic part of it, if you have certain parts that are metallic or not. That's it. That's all you need. And so I love the PBR workflow. So on the first part, what we're going to look at is the multi-scatter GGX, and then there's just GGX. So what I'm thinking is that this is multi-scatter and this is just a single scatter approach. I would assume that multi-scatter works really good. I don't see too many differences with multi-scatter, and what that does is it changes the specular model on the surface here, and most people are going with the GGX anyway. As you can tell, there's not any other choices because it's a very good specular model that's used. I would assume that in scenes where you have multiple objects that have a lot of specular reflection, and maybe even some transmission properties and stuff like that, that if it started bogging down, switching it over to just regular GGX during a single scatter type of event might increase performance. But if you only have a few objects in your scene, there is no real difference in performance between multi-scatter and single scatter. I would just take a look at this only if your scenes get really heavy and your renders get really kind of slow and you got a lot of reflective materials around there and you're like, oh, wait a second, let's just cut back to scattering a little bit. That's what I would use. The base color would be actually the diffuse, or what we're calling albedo now. You know, the shadeless type of color map that we put in there, or just a solid color. It's blue, right? And you can put it in any texture map that you want in here. You can actually load in any types of maps and stuff like that into this principled shader, and it will take it just like any other shader that you did. You just don't have to put in all the networks and the mix and stuff like that as much on this side of it before it goes into the material output. You do all that stuff before, and that's pretty much self-explanatory about base color. I mean, how much more can I talk about color? The surface, the subsurface, is an approximation. So we're going to go over here, and then I'm going to turn this off really quick so that doesn't work anymore. Now, what I mean by approximation is it is not true subsurface scattering. It just controls the shape of the subsurface around the object and through the object. It gives pretty decent results. But you know, if you use subsurface scattering, as in any engine, by using subsurface scattering, it introduces noise, just because it is calculating the paths and all that stuff. Yes, you can increase sampling and stuff like that, but you really don't need to anymore. The default denoise settings within cycles, if you bring a certain object into a certain degree of variance, and you don't need the variance all that low. I'll probably do another rendering thing later on how I've been able to optimize some settings and just make some of my renders fly. But some of those settings are scene dependent, of course. But subsurface scattering in almost any render engine will cause noise, and so it will cause noise here. So as we crank this up, do I still have my light on? That's what I'm wondering here. Where is my backlight? I should have a backlight. This should be working. Oh, because it's the wrong object. Duh. Let's do this. Let's do the correct object. There we go. So we crank it up and we can see, and it's just a simple. It's a simple ring here. Let's take this off of here, and I'll show you that it's just a simple ring. This one's not as deep as this ring in here, you know, and then we have a light back there providing the backlighting. So when we go in here, we can see that the subsurface, as you increase it, it penetrates further, and like I said, it's an approximation. There are true subsurface models that you can use, but they take a little bit longer to calculate, and this gives a pretty good result right off the bat. Now, what you'll notice underneath, though, is the subsurface radius. Now, set at 1 is completely fine, and I'm pretty sure there's a lot of settings that we can put in there and some sort of mapping about the radius and stuff. I usually don't ever mess with the subsurface radius. But this I found out was equivalent, like if I put this up to 0.1 and I put the radius down to 0.5, okay, All right. Well, what's the difference between that and then going over here and going to 0.5? It's about the same. It's about the same. I don't know if I can see too much difference between doing that. Okay, so it might be better used as a multiplier rather than just the amount of subsurface scattering in here, and this would be used as a multiplier to either add or take away some of this subsurface value. And I can see that the subsurface radius might be a little bit more valuable if you have this cranked up all the way and you needed some more or something like that. But other than that, it's going to increase your radius around the X, Y, and Z component. So I'm pretty sure you can fine tune certain areas. See how it kind of took that away a little bit on that component. And then, oops, and then you can push it higher. So you can actually adjust maybe either the colors. That must be, I mean, it kind of looks like the red, green, and blue component too. So I'm not really sure what the radius is doing at this time, and I'm sorry guys. There just isn't really an equivalent in RenderMan that I can use for this. Oh, there we go. Okay, I see what's going on here. So in some subsurface models, what happens, and here we go. So this is the thinner part, right, of the ring, and then we get thicker, and then we get like a little thin part here. In some subsurface models that are path trace based, what they will do is they will calculate a light path through an object, and they will try to add a specular component into it. And so this looks like almost like the red, green, and blue component. Not exactly a radius, but it will absorb or calculate the absorption of the light going through an object. So the thicker it is, the more of the light waves that it's going to absorb and the resulting stuff at the end. So say, for example, this is absorbing red colors, and so the only place where the red is getting through is on the very thin parts, and where it is attenuated more, we're getting more towards the cyan, which we would sit up here and see with some of these absorption types of things. But this is opposite of what I would expect, really. I would expect the actual color of the surface, I guess, being here and then be shifted more towards the red as it goes out to the side. But this may be like more or less towards the red, green, and blue component, so you can tint your subsurface however you want it to, instead of like just a particular radius. I mean, that's what we're seeing here is color shifting. So you can control your color shift by that, apparently. So that's pretty neat. But it does take certain things out of it when you have it like this. See, that looks like I just sapped all the red out of it, and all I have is the green and blue components. So that may be what it's more or less leaning towards, instead of like an actual, I don't know, radius dimension. So there you have it. That's basically it. And then you can tune your subsurface color, which is going to be completely different from the base color. So if we brought this back up and then you wanted it to be a subsurface like this, or you can match your base color and adjust it either up or down from that, that's basically it. It's regardless of what this color is. Okay, there may be a little tint thrown in there. I noticed that some came up there. And if I added the environment to it, you know, there's that, but the subsurface, as we crank that up, gets more towards the green because it's scattering more of the light through everything else. So that's the deal there. I don't really focus too much on subsurface scattering. Really, subsurface scattering adds a depth of reality to certain types of materials. But when you're in a situation where you may be far away from the object, or it just doesn't really contribute anything extremely special to the object, is always, or to the scene in general, it's best looked at as not doing anything at all with subsurface scattering and just keeping it off completely. Because it's just added render time. It's added render time, it's added noise. It can be added fireflies in places that you don't have time to calculate out, and so just leave it out. Not really necessary at all times, but it does play a good role within, like, you know, ears and thin parts of organic materials and things like that, or if you have really simple scenes. The metallic part is what we now use to describe the specularity or the reflectivity of a surface. It's not just purely going metallic or not. It's not just saying this is diffuse or not, because you can see that this already has a reflective property to it. I'll get to that in a second. That's the next little lobe down. But the metallic properties, as you notice, from here on down, these are all going to be controlled by, if you have textures, grayscale maps, okay, linear maps, and these are going to be color maps. Okay, the metallic part is going to determine the reflectivity of the surface. So basically, right now there is no reflectivity of the surface. It's not very much metal, and it's not just as simple as trading 0 and 1. Oh, there it is. It's metal. Okay, and there it's not. No. It's not that simple. Most dielectric materials, or things that do not conduct electricity, or things that aren't considered metals, have a reflectivity to them. And technically, it gets no greater than 0.04 or 4%. Like that. Didn't change much, right? Even if I turn the specular down, now you can see this. 0.04 is about right where it's at. This is completely diffused, but 0.04. That's the highest you'll ever get. And it starts at a range of about 0.017 and can go all the way up to 0.067 in range for your dielectric materials. Like that. That's about as far as it's going to go, ever. And yes, you can use that metallic component for that. When you are using metals, however, that range changes from 0.7 to 100%. Yes, that's a metal. But you need this specular component to define it even more. I want you to take note, though, as we go back down here like this, this component keeps this tint in there. So this is why we have the specular component. The specular component, this is what I was trying to describe in the last video that I made, is not anything about whether or not it's reflective or not. I mean, it kind of is. It defines the maximum intensity of reflectivity if you're staring straight at it, and it pushes the Fresnel out here. It defines the Fresnel and what it is. So no matter how metallic something is, even all the way out here, even though metals tint reflections, the reflections at the outer edges will always be, always, on the very outer edges, be white. You use the specular thing here to adjust the Fresnel. That's basically what it's doing. It's used as a replacement for index of refraction, pretty much, or a Fresnel input. And so you can dial that in anywhere. The default value of 0.5 is supposed to work for most, if not all, materials. And then, as you can see, you have that artistic freedom when I push that back and forth. Okay. It doesn't really do much more than bring it in just a little bit closer around the edges here towards the incident area. But as we lower it down, then you can see that there is nothing there. There should never be a material that doesn't have a white ring around it, around at least the very edges. Ever. It's just how the light is bending and hitting and reflecting off of here. So keep that in mind. This is in place of an explicit index of refraction, or Fresnel value. Now you go, but you have an IR here. Yeah, it does absolutely nothing for things from this point up. does nothing. Just sits there. I can go like this all day and it will do nothing. Do nothing. What are we gonna... We'll talk about that here in a second. The specular tint allows you to tint reflections. So if I come back here like this, you can see that as we get away from the metallic component of things, we can use also specular to define the specularity of this. But as you noticed, that as it drove away from being metal, look at the lights here. The lights here are getting a tint of blue. All metals will tint their reflections towards their base color. Dielectrics will not. Dielectrics down in this area, even though there might be a subtle tint in there, they don't really tint that much. It's not supposed to. It's supposed to be more along the lines of what the actual color is. It's a straight up reflection back. The specular tint is the artistic way of allowing you to control this and how much tint of the base color that you're adding into that surface. So when you increase it like this, then you're tinted back towards the metallic ranges. Okay, so it drives that tint back towards the base color. So you can actually artistically determine if you want tinted reflections or not. But technically, if you leave that specular tint down to 0, you're going to be fine with almost all your materials as long as you're driving them with a metallic. Roughness. Roughness is it's the heavy lifter look development. Basically, once you define how much reflectivity something has, whether it's a metallic surface, a dielectric surface, how much specularity it has, everything about the character of a surface is then defined by the roughness. And so this is the parameter that you really want to look at. Now you can have roughness maps to add a bunch of little random scuffs and scratches and stuff like that, which is completely awesome. But as we turn this roughness up, we can see that we lose some of the reflections. We have reflection blurring. Even if I go to the metallics, you see how that kind of, it blurs all the surface. We know what roughness is, and it spreads out even further until we get so rough that it becomes diffuse again, if it's 100% roughness. But nothing's really quite that rough, and things kind of hover around here, and you can tune it in any way you want. So even on, surfaces like this, even if I turn the specular all the way up and stuff, and I can define it like this. The roughness defines how much roughness there is along a surface, regardless if it's diffuse or metallic. So in a diffuse situation, basically what it's doing is it's making it look like, the old Fong and Lambert shading, where we used to put input values. Let's get that stupid thing out of the way. Where we used to have to input values in the glossiness channel. And so how much glossiness would determine how tight those specular reflections were, those specular highlights were, or how spread out they were. Okay, if it wasn't glossy, they'd be spread out. If it was really glossy, then they would become little tight slivers or whatever like that, have nice glints of light and stuff. That's basically what roughness does on the diffuse channel. On the metallic channel, it's reflection blurring. Basically taking all those reflections and blurring them out. So just like what we did here. If we increase this, you can see the specular hits, they kind of just spread out everywhere. And the metallic portion, it's reflection blurring. So it's basically blurring the reflections no matter what. No matter if it's diffuse material or a highly specular material. It works for everything. It controls a lot about the characteristics of everything you look at. You're either going to have a diffuse reflection or a specular reflection. There's no two ways about it. Okay, and some linear scale in between, but it's either going to be really reflective to you or not that reflective to you. And then the roughness will determine the light spread across the surface and pick up the imperfections and stuff. And that's what you want to use for that. Anisotropic. So anisotropic, or what people across the pond will probably say it better than I do, anisotropic, where isotropic means equal or even, and isotropic means uneven or unequal. And so basically this will stretch out reflections. Whoa, lost them there. So as you can see, I added some roughness just to get that. And so it's determining how much stretch there is. As you can see, they're stretching across this way. Okay, so we're stretching those. Normal, stretched. And then guess what? Its little buddy downstairs here, the rotation, allows you to rotate those reflections around wherever you want them to go. Now this might work better on a cylindrical object where you have like a brushed metal surface, and then you can, you know, if you add these anisotropic reflections and get it stretched, but it's going around the wrong way and you need it to go across the surface, usually like if this was the top and it was brushed with concentric circles, usually it'll have these wedge shapes that come into the center and then flare back out. Rotate them so they're going in the right direction. I like this implementation. There are some render engines out there that force you to define the X and Y component, how far X it is stretched out and how far Y. You know, why not just hit the one value and just let it stretch and then rotate it wherever you need it to go, right? I mean, why not? Sheen, I'm not going to do an example of Sheen too much. That's basically the grazing reflectivity in things such as cloth, maybe some leather, some other types of textiles and stuff like that. It's not really a specular reflection like this, but it basically is like that Fong or Lambert shading that I was talking about before, and adjust the spread of light across that surface. So when you are looking straight at it, like straight down on it, there isn't going to be anything that is going to show up as a sheen. But as you look at it at an angle or across the top of its surface, then you'll start to see that more and more. But it's more of a spreading of light, not an actual reflection as far as specular is concerned. And the sheen tint is set so that it picks up the tint of the base color of whatever the surface you're on. So sheen works very much like a metallic type of input, but we don't have that. I'm not going to show that right here. I don't think I want to. Yeah, it won't work on that type of surface. So we won't even worry about that right now. Now, clear coat is another type of surface that it's a secondary specular lobe. So you have your specular, say here. Let's just use this specular part here. And as you can see, I don't have any roughness, and so all these lights are being reflected pretty much evenly. So if I added a little bit of roughness to this and spread those out, but then I added a clear coat on top of it, there's a secondary reflection, and it is so dang subtle because it sits right on top of everything else, right? So imagine a car paint. All the car paints have, you know, multiple layers, and on top of it there's a clear coat. And a clear coat is what makes it shiny, and that nice little specular glint off of it and stuff like that. That's basically what this is doing. Let's just crank it all the way up just for the sake. And as you can see, it's fuzzy, but there's a thin strip here that isn't. Okay, if I turn this all the way down, then everything's good. But if I turn it all the way up, there's something here. Remember when I didn't have the clear coat on this one, all diffuse? Boom. The clear coat just adds the subtleness in there. Clear coat roughness defines the roughness of that clear coat. Apparently 3% roughness is good for a clear coat to start out with. But you can take it all the way down. You can have like these nice little sharp parts. And so if we bring our roughness back down to earth, to mean somewhere around there, then you have two different components. But it is so subtle. It is so subtle, but can add an extra dimension to your renders. Okay, remember, roughness all the way up. Look, the clear coat is taking over. If I took the clear coat away, that's completely diffused. So I'm going to take the roughness down. There's all that specular back again. If I add the clear coat back in, yeah, it's there, but it adds to it a little bit. Okay, that's basically what it is. And then you can add the roughness across the clear coat. if you have a clear coat that's really rough compared to the surface below the clear coat. Alright, so now we're getting down into the index of refraction area. The index of refraction does, like I said, absolutely nothing for things up here. But what it does do is it controls the amount of refraction through this transmission area. What is this transmission? Think of it as transparency. Because now it's transparent. Let's bring in the background. Now we can see this transmission and it's 100% transparent. Roughness will control this variable as well. So roughness is powerful, I tell you. So the index of refraction does this like it's supposed to. Okay? The default of 1.45 is pretty good for many things. If I turned it down to 1.33, I think that was flint glass or acrylic. Changes it just a little bit more. Look up all your little stuff online about what your index of refraction should be for whatever material you're using. Put it in there and it'll behave just like it needs to. But this is the only place where it works. Okay, and then we can have its scale its transmission down depending upon how transparent you want it to be, even bringing it down to an area that may be considered translucent. And that's where we make those changes. Now, is there any difference between transmission and the glass shader? As far as I can tell, no. As far as what some people say, the calculation is faster using the principled shader. Principled shader may be optimized a little bit more than the glass shader, but for simple scenes, this doesn't really do. I mean, it's not much different. Okay. Now let's get back to the transmission down to 0, and then just to remind you that this does absolutely nothing for anything else. It is only used for the transmission. I wish there were, like, in some of these things, I wish there were separators. Like, you could put a line here that would be separating these settings, and the separator of these, and the separator of this, and this, and this, and so on and so forth. But remember, the IOR, if you're jacking around with it and you're not getting the results that you're looking for as far as the index refraction or the Fresnel effect across this surface, remember you're going to be using Specular to drive that. You're going to be using this. Okay? And your IOR is only going to affect transmission. Okay? Obviously, the more metallic something is, you can't be transparent. I mean, there are metals that are transparent on levels of atomic radii, but that's about it. But this is the only place where you're going to find that component working. So I hope that helps some people with some of their some of the surfacing and understanding some of the principled shader. I do know that I like using simple setups like this with kind of complex backgrounds to test reflection and the index of refraction and all that other stuff. I'm sorry I didn't set you up the Sheen tint thing. Learn about the subsurface radius, you know, as we went, but really the principled shader should, you know, cut down your work. I just wish, and if anybody from the development ever sees this, I'm kind of getting tired of having tooltips that don't have any explanations for stuff, because it really leaves people in the dark, and then you have to really figure these things out. And since I just had a surgery and I'm off work for about 2 or 3 weeks, maybe longer, I have time to play around with this stuff. So I thought I'd just send it out there into the world and let you know what I came up with. If you have any questions, go ahead, hit me up in the comments section. I'll try to get back to you as soon as I can. Other than that, I'll just keep on doing what I do, and we'll just keep on putting these out as best we can. All right. Thank you.